Hi, everyone. My name is John Simon. I'm the Product and Applications Manager here at Intrepid for Automotive Ethernet tools, and I'm here today to talk to you about next generation of Automotive Ethernet. So if you are familiar with any of the IEEE or other in-vehicle networking conferences, you might have seen this diagram before, and it shows the history and trends of in-vehicle networking. So you can see in the bottom here, some of the early days back in late 80s, early 90s. We started with K-line and ISO 9141, CAN, sub-megabit networks. And we've progressed all the way up through gigabit, and now we're talking about multi-gigabit. You can see the different network topologies, point-to-point networks, buses, switched. It's just very interesting to see the trends, obviously, all going higher and higher, but we also have some trends at the bottom for lower bandwidth networks. Before I go into the types of tools that we supply, I can't assume that everybody is familiar with Automotive Ethernet, so I'm going to discuss some of the different pieces of tools that are used in instrumenting Automotive Ethernet. And the first type of tool is used for mixing physical medium, and they're called media converters. And the reason this is needed is because when you combine multiple networks with different types of media, you can't just plug them together and everything works. As it turns out, you can do this for gigabit and 100 megabit Ethernet networks at home because they were designed to be backward compatible. You can plug in an 8-wire 1000 base T PHY to 100 megabit, 100 base TX PHY, and they'll auto negotiate down to 100 megabits. But that doesn't work for every technology. For example, it's not going to work fiber optic to electrical connector. You can't plug an optical fiber into an electrical socket. And unfortunately, this does not work for Automotive Ethernet and standard Ethernet. T and TX are not compatible with 1000 base T1. And T1 is the designation for Automotive Ethernet. It stands for a single twisted pair, where the other suffixes can stand for 4 twisted pairs, 2 twisted pairs, optical interfaces, etc. So what's needed is something called a media converter, and strictly speaking, it takes one media and straight pipes it through to another media. In the case of Automotive Ethernet, one of our first devices is called the RAD-Moon, and it takes a PHY or physical layer device for Automotive Ethernet and connects it directly to a standard 100 base TX Ethernet, which is a 4-wire, 2 twisted pair physical medium. So today's technology is moving primarily from 100 megabit, 100 base T1 to 1000 base T1. We support this development with this with something called the RAD-Moon 2. It's a 1000 base T1 media converter. It also supports 100 base or 100 megabit. It uses a Marvell PHY and directly connects between 100 base T1 or 1000 base T1 to 100 or 1000 base T. To use this device, it's really just plug and play, but there are a couple configurations that are associated with it. One is the way PHYs work. One of them is a clock master, supplies the clock, and then the other one synchronizes with that clock. And this can typically be in your home Ethernet. This is auto negotiated. Typically in automotive networks, these are engineered networks, meaning everything's statically defined up front. This is a static setting, so you can cycle between master, slave, or auto negotiate. You can also set the link speed. Again, home networks auto negotiate the speed to the highest speed. In automotive networks, this is typically statically set. So you can statically set this with buttons on the user interface. There's also some indicators on there that give you an idea of what protocols are passing through the device. So whether they're IP communication, GPTP, which is a time synchronization protocol, and then AVTP, which is streaming media for automotive networks. And then lastly, there's a 12 level SQI, Signal Quality Index bar on the side of this. And this gives you an indication of, on a scale of 1 to 12, what the signal quality is. And this correlates with something called a bit error ratio. And that's a measure of how the integrity of the electrical signal and of the PHY and its ability to decode that into digital, basically bits and bytes. Other features or characteristics. So this is powered by either a USB 3 port. It needs to be a USB 3 because it can draw upwards of 1 amp. So a USB 2 or a port that's not fully rated, you might not fully power, and you might get erratic operation of the device. Or you can power it with a barrel jack with between 4.5 and 40 volts. We use the MACnet 1000 base for 1000 base T1. There's also Rosenberger, which is frequently used by some of our customers. And we're working on a translator board that has MACnet to the Rosenberg HMTD for those customers that need that. And lastly, one very important thing when you're doing testing, either ECU development or in vehicle network development, is being able to have visibility into the PHY. Specifically, are there errors? Are there other problems with the behavior of the PHY? And all this information is located in registers in the PHY, which you can read through over USB, either using Intrepid's Vehicle Spy software. We have something called PHY Dashboard, which is a very basic interface where you put the register address and you can read or write information, or open source API. And so this, you can read things directly, like the signal quality index. You can read error counters. You can read, they have histograms of, I'm sorry, I'm getting that mixed with switches. So yeah, signal quality, link status. There are also some registers in there to tell you like time to link and different stages of the linking process as PHYs connect with each other. Now, the latest development in automotive Ethernet is multi-gigabit, multi-G based T1. So in prototype stage, we have the RAD-Moon 3, which is a successor of the RAD-Moon 2. It uses a Marvell 88Q4364 PHY. And similar function, but the higher speed, so it supports 2.5, 5, and 10 gigabit connections from from base T to base T1. It does not support gigabit, so this supports 2.5, 5, and 10, but it is not backward compatible with 1 gigabit or 1000 base T1, and this is a limitation of the PHY itself. Similar user interface. You see the PHY configuration and status. You see link speed, the configuration, the status and activity, the same SQI indicator. Other features very similar to RAD-Moon 2, the difference being, one difference being that it's only powered by a barrel jack. USB 3 is rated for 1 amp, and with the multi-gigabit PHYs in this, it's going to exceed 1 amp, and so it would not be a reliable power source. So strictly 5 to 40 volt source connected with the barrel jack. We moved to the HMTD Rosenberg connector. It's rated for multi-gigabit traffic. There's also, my understanding is that TE is working on an equivalent part for that called GemNet, I believe. So they will be intercompatible. Same PHY register monitoring. And in this case, we had an extra button in the interface. So we're going to make this button accessible by our API. So you can use it, for example, turning on test modes, switching, however you choose to write your test application, you can use this as an input to change modes or trigger an event. Some history for people that maybe are coming from a CAN background or new to Ethernet. Why did we start using switches in the vehicle? We go into a lot of more detail in our Ethernet class regarding this, but for the purposes of this, I'll just kind of give a brief overview. Well, fundamentally, network efficiency. And what I mean by that is it's no longer a shared bus, it's a switch network. And so you're effectively conserving bandwidth on each segment of the network, and you're forwarding Ethernet frames only where they need to go and not on parts of the network they don't need to go to conserve bandwidth. So each physical connection on the switch network is its own independent link, and so there's no collisions. So here, just for an example, we have a switch connecting a head unit, maybe 2 video displays in the back, and an amplifier, and we might have 2 different streams going. We'd have a stream going from the head unit back to the amplifier through the switch, and we have another completely independent stream going from one video display to another. And each one of these streams is 100 megabits full duplex. So what you're seeing here through a switch is you have an aggregate bandwidth of 400 megabits, despite the fact that each link is only 100 megabits. So this is really the main purpose or importance of the switch, is to conserve bandwidth across the switch network. Another thing a switch can do is enable what's called quality of service, and that is basically treating traffic or giving traffic certain levels of quality of service in terms of latency or reserve bandwidth or redundancy. And so the different types of quality of service a switch can enforce, first and foremost, dropping bad frames. So one way to conserve bandwidth is to not forward corrupt frames across the network. So if a switch receives a corrupt frame, it will drop it. There's a term called VLANs in Ethernet, and this is another way to restrict traffic based on tags or a class particular characteristic of the Ethernet frame that you can explicitly restrict or give access to ports or on different parts of the network. So something on, say, like VLAN 1 is going to be restricted or can be restricted on ports that are part of VLAN 2. You can also do traffic prioritization. The switch has independent queues inside of it, and so it can read each frame that comes in and do some inspection on it and decide where it is in relative priority from one type of traffic to another, and then they go into queues that can be there's a host of different ways these queues can be managed. It could be a strict priority of the highest priority traffic must be completely transmitted before lower priorities. There's also a round robin and a weighted round robin, but this is another form of quality of service. You can do something called ingress limiting, and this is where the switch can restrict the rate of the traffic that enters the switch. This could be in terms of, it could be restricted based on frame size, it could be restricted on frame rate, it could be restricted on bandwidth. And then there are also, you'll hear the term ABB-TSN, that's audio video bridging and time sensitive networking. This is a number of different protocols that are specific to synchronizing the network, all the devices on the network to a common time base, and then providing quality of service for time sensitive streams in terms of bounded latency and determinism and even some redundancy as well. And so switches are constantly evolving to add additional features and functionality as the IP gets more complex. They're adding more features into the silicon that in some cases may have been done in software in the past. So in automotive Ethernet, or really any Ethernet, since it's not a shared medium, you can't just tap into the bus. You can't stick a pin through a wire, put an alligator clip and monitor. So there's some complications that are associated with the the higher bandwidth and being in a switch network. So one method of instrumenting an Ethernet network is to use port mirroring. And this is where you would connect all the devices on the in-vehicle network to the switch. And then that switch would have a single port called a mirror port. And you can configure that switch to send copies of everything received on all 4 ports, in this case, ports 2 through 5, to the computer. There are some drawbacks to this. Switches are a device that are called store and forward. And what that means is the entire frame has to ingress or enter the switch before it can be transmitted out another port. And the reason for this is because of the quality of service of dropping bad frames. For the switch to be able to identify a bad frame, it needs to evaluate the CRC or the FCS at the end of the frame and verify that it's valid or not. So the drawback with that is there's latency. So longer frames take to get longer time to enter and exit the switch. Shorter frames, conversely, are more direct straight through. A switch won't forward bad frames. There are some advanced switches, I think you can force them to forward bad frames, but typically they will drop them because it's in the specifications, that's their requirement. So if you're instrumenting a vehicle network and there are bad frames floating around and you're using a port mirror, you may or may not see the traffic that you're looking for, or the traffic that is causing the problems because it's corrupt. If timestamping is a concern, or precision timestamping, if you do this, there's really no real precision to it. The computer or the operating system is going to timestamp it whenever the frame reaches the stack that does that in Windows or Linux or whatever. And so there's any number of different latencies or non-deterministic things going on that will affect that. The other thing that can happen is frames may not arrive in the same order they actually arrived at the switch. So switches, as I mentioned, they have the queuing. Depending on how the queuing's set up, certain frames might be forwarded before the other frames by design or by configuration. The other problem is what I mentioned about the store and forward frames. So if you have one large frame that arrives first, it's going to take a while to ingress. You could have, half a dozen small frames that'll shoot right through the switch to your computer before that large frame even presents itself. So you have that behavior to deal with. And it really depends on your use case. In some cases, you can interpret the traffic despite these shortcomings. But if you need precision timestamps and you need to know that the messages are being displayed in the order they were received at the switch or in the network, you need something called an active tap. What an active tap is a man in the middle. So instead of connecting all the devices to a switch, you insert this active tap between ECUs. And the active tap would intercept the frame from either of these ECUs immediately and then forward it. And in the process of forwarding it, it timestamps it when that frame hit the wire. The FPGA does that. And then minimal latency. So this device can be configured as a cut-through device if you like. It doesn't have to do store and forward because it's not a switch. It doesn't need to enforce the quality of service of dropping bad frames. In fact, you don't want it to. You want it to pass bad frames back to the computer and to the other device. So you can configure it as a cut-through. You can also inject traffic with this. One thing you can't do with the switch is strategically inject traffic. You can send traffic into the switch from your computer, but the ports, the switch is really going to decide where that frame goes. You can't really force it. You can't inject it between two frames. And this is something with an active tap, you can do this because you have control at the MAC level down in the hardware in the FPGA. And again, bad frames are encapsulated and forwarded to the PC. So you have evidence of something going wrong. And this is something that can be masked by any number of things. For like TCP was designed to basically request retransmission of frames. So you could have problems, underlying problems that there's no evidence of. You're not going to see any evidence of this because the bad frames are thrown away, but the layer 4 protocol is going to request them, and the information arrives ultimately where it's supposed to. So for tapping, we have something called a RAD-Galaxy, and this is 6 active taps, because when you're instrumenting a vehicle or like a bench or a breadboard or subsystem, you're interested in what's going on the whole network. You don't want to see what's going on between just the switch and the head unit. So it can tap up to 6 different links of the network. In this case, it's showing a gateway connecting 6 different ECUs. And so you can use these, it's got 12 ports. You can use them as 6 active taps, or you could use them discretely or independently just as ports to an ECU or device or device under test for sending and receiving directly to it. It also has some legacy networks built in to log CAN, CAN-FD. So this is also logged at the same time base as all the Ethernet networks. So you can see correlation of events on one network and what correlates with events on another. It also supports diagnostics over IP. Automotive voltage ranges from 4.5 to 36 volts. And it does include a standalone data logger in the form of an SD card. So that was 100 base T1, moving to 1000 base. RAD-Gigastar is something that was released, went to production a few years ago. And it's a dual 1000 base T1 active tap. So it has 4 ports, Ethernet ports on it. 2 of them are 100/1000 base T1 ports, Automotive Ethernet. And then we have 2 SFP cages. And if you're not so familiar with what an SFP is, it's basically a slot that accepts an SFP module. And that slot or that module can have any PHY or any physical layer that you care to choose. So it comes with 1000 base T PHYs or SFPs, but you can purchase 1000 base T1, you can purchase optical, you can purchase 100 base TX. All of those can be plugged in the slot, and you basically have the physical layer of your choice. So the primary function of this device is an Ethernet active tap. You can use any 2 ports. So you can have the tap pairs of 100 or 1000 base T1 tied together in a tap. You could tap from 1000 base T1 to whatever PHY you have in the SFP. So you can tap between T1 and T. You can tap between T1 and optical. And then you could also tie the SFP's ports together as an active tap. And you can use those taps simultaneously, connecting to host PC using USB 3. Also some legacy networks for logging, 6 CAN, 1 LIN, 2 FlexRay, receive only, and diagnostics over IP. Also has onboard storage up to 512 gigabits. It does, I need to elaborate on the limitations of this, because you have up to 4 gigabits of 4 aggregate gigabits of traffic through this. It is an SD card, so you're limited to 50 or 400 to 480 megabits per second logging. This is also it is an SD card, but it's not customer serviceable. It's something that's installed when the device is manufactured. So different applications of the Gigastar, first and foremost, an active tap, so you can use it between 2000 base T1 devices. You could use it as a gateway. So you can have the embedded processor in the RAD-Galaxy, receive messages on one network and forward them to another network. I have a presentation later on today about Automotive Ethernet gateways but this would be one application of that. basically tying any of the networks it has together with some logic and some rules inside to decide what information goes where and in what format. So for another example would be you could do on-the-fly network address translation. So you could have frames coming in with one MAC address, source MAC address, and having the egress with a different MAC address, or really anything in the header you could replace. You could replace the IP address, you could replace the logical port, anything within the Ethernet frame is fair game. Again, standalone data logging. You can use ECU system level automated testing. So again, the embedded processor in there, you can program the scripting and have it simulate ECU. You could have it if you're doing like avenue testing or things like that, where you have a strict step-by-step, kind of like a state machine type of thing. It lends itself very well to setting up a state machine of this message comes in, do this, measure this time, etc. Support Ethernet, so you have the different protocols, SOAD, diagnostics over IP, flashing, Automotive Ethernet or KNFD. The embedded function blocks, that's what I was alluding to with the standalone scripting, the embedded processor. Function blocks are GUI driven, basically state machine generator. In terms of switch products, RAD-Jupiter was our second Automotive Ethernet switch. It's now the only switch that we have. Our first switch is out of production now, but this one's the 7-port managed switch. And so the ports that it incorporates, it's got 500 base T1 ports, and then it has 2 gigabit ports. One port is both these gigabit ports have a MUX. So you can configure them to be one of 2 different physical media. So one of them, you can switch between Automotive Ethernet, 1000 base T1, or to 1000 base T. And then the other one can either be 1000 base T or switch over to a USB bridge, which when it's configured as a bridge and you plug it into your laptop, it basically enumerates as a network adapter on the in Windows, just like one of those USB to Ethernet dongles. The quality of service that I discussed earlier, it supports ABB TSM protocol, so it supports being in GPTP, that's a generalized precision time protocol. It can serve as a master or a slave, and then it can fan out into other devices on in the clock domain. It also supports credit-based shaping, which is a means of shaping traffic so that you guarantee certain bandwidth for, say, high priority stream, but it also adds some fairness to what's called best effort traffic, or traffic that doesn't have any priority or quality of service guarantees. And so it kind of prevents bursting of high priority traffic. It's got something called TCAM, and if you've heard the term packet inspection, that's the technology behind it. So basically, you set up bit masks of the type of frame you're looking for, and if a frame comes in that meets that bit mask, then that fires off a rule or an action within the switch, and that could be to forward certain traffic or drop it. It could be change the VLAN information or change the priority, or forward it to a specific queue, like override the destination of the frame. You can do things like whitelisting and blacklisting addresses or certain types of frames. You would do that through TCAM. You can set up the ingress rate limiting I was talking about. They can be based on frame size. And also going through, there's a cut through mode where you can set this up. So to avoid the store and forward the latency I mentioned before. And this also has a couple legacy networks on it, CAN and LIN, with an embedded processor that supports the scripting, the function blocks I mentioned before. So our new switches that are in development right now, we have a prototype outside. Larger switches, more features, higher bandwidth. So this one is a 10-port switch, upgrade from a 7. It's got 6,000 base T1 ports, two 10 gigabit ports, 10G base T, and then a USB to gigabit Ethernet bridge. Same quality of service I mentioned as the Jupiter. One difference being it supports time-aware shaping. I don't have time to go into that now, but it's kind of like a means for adding determinism to an Ethernet network. It's a form of TDMA, time division multiple access. Per stream and filtering and policing, another form of ingress rate limiting or egress rate limiting. Also has deep packet inspection, ingress rate limiting, so the same features as the, it's a Marvell switch. It's just the next generation of what was in the Jupiter. This has the 88Q6113. Also have PHY and switch register access. I mentioned on RAD Moon 2 and RAD Moon 3. You had access to the PHY registers. On this one, this device, you have access to the PHY and the switch registers. So the switch registers have counters, error counters, statistics on the information, the types of frames coming through the switch, counters for high bit error rates. It's like hundreds of pages of information that you can dig through the spec and find. Also has a couple obligatory CAN and LIN networks and function block support. We made a derivative of this switch, called it RAD Epsilon-T, T standing for 1000 base T, and it's identical switch. The only difference is we swapped out four of the 1000 base T1 ports to 1000 base T ports. You can see a picture of it up here in the upper right. It also, one other difference is instead of RJ45s for the 10G base, the base T networks, we're using an industrial connector, an IX connector, primarily for space reasons. We couldn't fit that many RJ45 jacks on the front face of the board. It also has power over Ethernet on the base T ports. And then same as RAD Epsilon, all the same features, it's the same switch. And then another derivative of RAD Epsilon is RAD Epsilon Express. This is a PCIe card that integrates the same switches in the other RAD Epsilons. The physical layers we've incorporated are 6,000 base T1 ports and two 10 gigabit ports. I have a prototype sample out there if you're interested to take a look at this as well. Again, same as RAD Epsilon. All the same features because it's the same switch. The main difference is now it's a card, you plug it into the PC, and then with the Linux driver, you basically have a direct PCIe high bandwidth port directly into the switch that's connected to all these other physical media. And then the large switch we have in development is a 19-port managed switch. It's essentially two of these switch ICs in RAD Epsilon. Daisy chained together with a 10 gig port, and that gives you 16,000 base T1 ports, two 10G base T ports, and a 1 gigabit SFP available. Same features, same switch, same features. We do have some 10 base T1 devices in development. If you're not familiar with 10 base T1, Colt's going to talk about that, talk about that later in the day, I believe. But basic rundown is it's slower speed, 10 megabit. It's a multi-drop or a bus like CAN, so you don't have switches. It's half duplex, and there will be confusion, but we're here to help. There's a lot of things that when there was a switch from CAN to Ethernet and like regular Ethernet, there was a lot of difficulties in understanding the differences and what works, what doesn't, what works differently. But we're here to help. It's no longer simply connecting for a media converter. There's no longer connecting two media interfaces together to two PHYs. There's something called PLCA that Colt will talk about. This is the arbitration or collision avoidance that is used in 10 base T1S because it's a shared media. So if you have any use cases coming up or are just interested in technology in general or what we're doing, talk to your sales rep. I didn't want to put anything in here too prematurely because it is still in development. And we're also working on MACsec products as well. If you're not familiar with MACsec, it's layer 2 security, hop-to-hop security at layer 2. So it can do authentication, origin authentication. It can do encryption, and it does this by inserting some security information into the layer 2 header of the Ethernet frame. And so this is all done on a Mac level in hardware, and there's software involved as well with key exchanges, etc. But if you have, again, also, if you have any questions on this, use cases, or just the technology in general, talk to one of us and we can tell you, answer your questions and give you an idea of what direction we're headed. We're definitely interested in the directions you're headed.